if you remember, we were using a technique that allowed us to transform linear differential equations into algebraic equations. And we were making a kind of dictionary, passing from the T domain to the S domain. So you have for instance, a differential equation like x dot is equal to minus 5x plus u. Okay, and then you pass this to the S domain by, so here we are in the time domain, and we pass to the S domain where the derivative is just multiplied by S. And this becomes minus 5s x of s plus u of s. And I can solve this with respect to x. X of s is what? What is x of s in terms of u? The solution of this equation in terms of, for x with x in terms of u.
1 divided by s plus 5.
S plus 5, u of s. And then I told you that we had, there was an interpretation in terms of making s equals to j omega, because this function here is a kind of gain that depends on the frequency. This would be 1 j omega plus 5, and the static gain of the system is the modulus of this quantity. And if you apply, if u is a sinusoid, u a sinusoid, so ut sinusoidal, then x in a steady state, that is to say, after a while, also a sinusoid with of the same frequency. So if this is, say, ut if ut, for instance, is sine of omega t, then xt is, again, let's call it a, sine of the same frequency plus a phase, and a is the modulus of 1 divided by s plus 5, and B and the phi, the phase, is the argument. This is not S, this is J omega. Okay? And then we said also another thing. If we compute this gain, if we compute this gain, then A is 1 divided by the square root of omega square plus 5 squared. But you can write this as uh, 1 divided by 5, and here 1 divided by 5. That is to say, this is square root of omega divided by 5 squared plus 1. Because here you have 1 divided by 5, it's the square root of 1 divided by 5 squared, multiplying omega squared plus 5 squared, so you get this. So for omega, let's clean up this stuff. If you do a plot of the gain as a function of the frequency, what you get, for omega very small, you get 1 divided by 5, which is 1 divided by 5, okay? So for small, in the low frequency, you get something like this. But then omega starts getting bigger and bigger, and the denominator is decreasing. And this is especially true when omega passes by 5. So if you have 5, actually this is doing something like this, and going to 0. Linear units. Okay. So for a frequency below this 5, you have a more or less constant activity of this system. But for higher frequencies, the system does not respond because the gain drops. Okay. So if you think of U that is decomposed into many sinusoids. If you have an arbitrary signal, you decompose it as a sum of sinusoids. If U is periodic, it's a Fourier series. But even if it is not periodic, you have the Fourier transform that allow you to write any signal, any continuous, even a discontinuous signal, as a sum of sinusoids. So some of these sinusoids will be amplified within this range. So sinusoids up to, say, here, the system responds to these sinusoids, but not to these other sinusoids. Here, the system does not respond. Suppose that u is a step. U of t is 1 for t bigger or equal to 0. And x of 0 is 0. So you have time, and you have applied something which is constant. This is u. Now, x start at 0. Okay? And it's 0. So what is the slope? What happens at this moment? Where is x going to evolve? If you want to do a plot of x in red, if you are at time u, the value is 0, but then there is a derivative. What is the derivative for x of 0 equal to 0?
1.
1. Why 1?
According to that expression, minus 5 times x is 0 because x of 0 is 0, and then plus u, which is 1.
Okay, so this grows a little bit with the slope 1. And then what happens? The slope stays the same, increases or decreases? Now x is a little bit bigger than 0, and u is the same.
It depends on the value of x, right?
Right, but you know that x is positive because it increased a little bit. So what is the slope now after reaching this point, say? Is the same slope? Bigger slope? Higher slope? Three possibilities. Each one of you can vote for one.
A smaller slope.
Why a smaller slope? Because u is still 1.
Yes, now we are subtracting something.
And now we are subtracting something, so it's a smaller slope. So this still increasing, but now it's something like this. And then here, what happens? Faster, accelerates, same slope or lower slope?
Lower?
Lower, because x is even bigger. Okay, so you have something like this. It never touches. Well, where does it approach? It's probably not going to u, but it's going to, what is the steady state? In steady state, what is the value of x? Suppose that this is 1. In steady state, what is the value of x?
1 divided by 5.
So 0.2, good. 0.2, okay, this is, so it will go something like this, okay? So this is the static gain. This is the static gain. So you make x dot equal to 0, you solve it with respect to x in steady state, so it's 1 divided by 5. If you make everything here equal to 0. Now, think of this as something in which u enters and x exits. Okay? And your input is something that is very fast because you have even a discontinuity. So you need a lot of sinusoids to approximate this discontinuity here. High frequency sinusoids. Okay, the system, the rate of, what is the rate of change here? What is the rate of change here? At 0. It changed from one value to another in just 0 time. So the rate of change is what?
Infinity.
Infinity. That's infinity. It changed from between two values instantaneously. That's infinity, rate of change. So this system is very fast, okay? And now look here. The frequency, the high frequencies, if you think of U as decomposed in sinusoids, the high frequency sinusoids are very much attenuated. Okay? So only the low frequency, and that's why you have something that has this shape. So instead of changing instantaneously, it changes slower. Okay? It changes slower. If this was second order, I could prove that it was even slower. So instead of having this here, if I amplify, I have something like this. So there is a discontinuity on the derivative. For a second order system, it would be something like this. So continuous. This is discontinuous. The derivative here is discontinuous. This is continuous. So because probably this would be faster. Okay? Think of a second order systems as two first order systems in series. So one cuts high frequencies values and the other even cuts even more. Okay, so there is this. Now we have what? We have another issue, which is stability. So we can using this technique, okay? So you have two domains, the time domain, and you solve the differential equation and use these arguments based on the derivative and so on. And you have another domain, which is the S domain. And here you give interpretations in terms of frequency. But you can also give interpretations in terms of stability. It's, you want to make questions? Before going on, let's justify a little bit about this S story. Okay, let's justify this S story. Can I clean up this stuff?
Yeah.
So I have, let's start with my differential equation here. And assume a solution of the form. So I say x of t is some constant times the exponential of st. Okay, where s can be complex. So let's find conditions for s. C is a constant. Let's see if this can be a solution of our differential equation. So we have to show that our function verifies the differential equation. Let's forget a little bit about the initial condition. So what is x dot? If x is this, what is x dot? X dot is what? What is the derivative of the exponential?
SC.
Is s. S what? C?
C.
Uh-huh.
And the exponential of ST.
Okay. Okay. Looks familiar because the story of the derivative means multiply by s. Okay. Now, let's plug this stuff there. What you get? X dot. X dot is s c exponential. Okay, let's forget about u. Okay. Suppose that I don't have any u. So I just have x dot equals to minus 5x. SC exponential of, I could have a u, but it would complicate the computations. Equals to what? Look at the differential equation. What does it tell you?
Minus 5.
Minus 5x.
See, this is an S. C. And then exponential of ST. Okay? Now,
I didn't understand. Why do you have the S?
because I'm dummy. Is it correct now?
Yes.
Thank you. I could say it is to see whether you are attentive and understanding what I'm saying. But the real truth, the plain truth, and the sad truth is that I committed a mistake. Okay, now it's correct. Now I want to have a condition on S. So maybe I can write this in this way. S C exponential of ST plus 5 C exponential of ST is equal to 0. Now, conditions for S. How can I get a condition for S? How can I write this expression? I know that all this stuff is 0. So
S is minus 5.
sorry, S.
Equal to minus 5.
Okay, so I can write that S plus 5 is C exponential of ST equal to 5, and then you claim that this is equivalent to S plus 5 equal to 0. Is this true? You have a product of two factors, S plus 5 and C exponential of ST. Now, C is a constant, should be different from 0, otherwise X is 0, okay? X equal to 0 is a solution, depends on the initial condition, but let's rule that out. So assume that C is different from 0. What about the exponential? We know it never vanishes. So C exponential, this term here never vanishes. So you have something that is never 0, multiplying by S plus 5, so S plus 5 must be 0. Okay? This is the so-called characteristic equation. Okay. And of course, s equals to -5. So we have a family of a family of solutions depending on c, which is xt is equal to c exponential of -5t. Okay. And then this c depends on initial conditions. For instance, if x of 0 is 2, what is the value of c?
2.
2. Because make t equal to 0, this exponential becomes 1. So in general, xt is x of 0 exponential of -5t. Okay, so when we are doing this trick of considering gas and so on, we are actually saying that all our signals are in one way or another exponentials. And exponentials can be can be a constant, can be an exponential, a real exponential, can be a sinusoid. Okay. Actually, what we are using here is the Laplace transform. Okay. Actually, the first guy who invented this, he was a guy called Heaviside. He did not call it Laplace transform, he called it operational calculus. So he was writing the differential equations for circuits and then was solving the differential equations using this technique. It was a kind of game to him, where you have an S. Now, you have the problem of going back to the time domain. And for that, you have tables. You have tables that relate this stuff with the time domain. So you have a kind of dictionary between S and T. Okay. But the justification is that you have actually, you are assuming that you have solutions that are exponentials. Okay. Or generate exponentials filtered by some other signals. Okay, now we can also, let's see a second order example. Let's see a second order example. Any question about this stuff?
No.
So suppose that you have a system which is a I don't want to make so many computations, but let's write the differential equation not. So you have, okay, instead of using x, I use the letter y. I will save x for state. You have this differential equation. And you have some initial conditions. Okay. Now, let's find out the solution. So if we apply the story of the S, what does it become? The second derivative? The second derivative is the first derivative of the first derivative. So what is in the S domain, what does the second derivative becomes?
S squared.
S squared. Y, I know that is Y of S, so I don't write it down. Plus what?
5s y.
5 sy plus you see any derivatives?
2y.
2y equal to 0. Okay, so you can put y in evidence, so you get s squared plus 5s plus 2 y is equal to 0. Okay? So it must be, since y can be anything, it must be s squared plus 5s plus 2 is equal to 0. This has two solutions. Let's compute the solutions. Let's do it here. So S12 is equals to what do you place in the denominator?
2.
2. And here?
Minus 5.
Minus 5. Then
Plus or minus?
Plus or minus square root of?
Minus 4 times.
No, it's
No?
b squared. If you have.
Yeah, b squared, yeah, 25, yes, 25.
So 25.
Minus.
Minus
8.
2ac.
Yeah, minus 8.
Quadrado menos 4ac. 4ac.
Yeah, minus 8.
Minus a is 1, c is 2, minus 8. Okay? And the square root of 25 minus 8 is that we can compute. We're going to have my it's 4.1. So S12 is minus 5 plus or minus, let's say 4, okay? Divided by 2. It's 4.1, but approximately equal. So you have S1 is equal to minus 9 divided by 2, it's minus 4.5. And S2 is minus 1/2. Okay? So what do you think y will be? Y of t is going to be what? Suggestions. Remember that y is, in the first case, it was one exponential. Now we have two possible exponentials. So it's probably a linear combination of exponentials. So you have a constant, let's call it C1, exponential of minus 4.5t plus another constant exponential of minus 1/2t. Do these solutions goes to 0 or not? You agree that this is a solution or no? Actually, what I was doing here was, I mean, I could start with the exponential and so on, but I just use that rule. And why is the exponential? So I put y in evidence, which is the exponential. If y is not 0, then I get this 0. So this gives me the possible exponents. So this will be the solution. And C1 and C2 depend on the initial conditions. Now, in general, does y go to 0 or not? Always. When time goes on.
Yes,
Yes, what?
it goes to 0
Why?
because both exponentials go to 0.
Yes, because they are negative exponential. So the trick is that S1 and S2 have negative real parts. Actually, S1 and S2, that in this case, they don't have any imaginary part. It's just a real part. But both real parts are negative. You don't agree, José and Cave?
No.
So
It is always go to the 0 if the S1 and S2 would be minus. Yes, this is like a,
yes, because you know that the exponential, what
Yeah,
is
yeah.
the graph, or what is the graph of the exponential? If you have t, and you have the exponential of t here, where do you start for t equal to 0? This is t equal to 0. Where do you start? Cave.
yeah.
Well, where do you start for t equal to 0? What is the value of the exponential?
So it is 0. So
No, 1.
1. Sorry, yeah, it is 0 is 1. Yeah, exponential 0 is
1.
Yeah.
Okay? And
Yeah.
then, as a good exponential, it grows.
Yeah.
But if you have, it grows, let's make a better plot. Something like this. Okay? Now, if you have exponential of minus t, what happens? For t equal to 0, 0, what is the value of e to minus t?
So it
Well,
would be like
it will also be 1 because if you
Yeah.
make t equal to 0, minus 0 is 0, so it's 1. Okay? And then it decreases. Well, is this a big miracle that it decreases? Look, if you interchange t by minus t, it's like swapping the page. Look at my hand. You swap the page, and what the blue becomes the red one. That's the effect. If you rotate the page around the vertical axis, t becomes minus t. So what was the increasing now is decreasing. Okay?
yeah, now I got it now. Thank you.
So negative exponentials go to 0. If you instead if you have, say, 2t, this is faster. This grows faster. If you have say 0.5t, this goes slower, but always increases. What is important is the sign. And also here, it's faster or slower. Okay, so all the solutions, you have here a negative exponent and here a negative exponent, they go to 0. In chemistry, you use a lot of exponentials and logarithms. You are always making computations with exponents, so you should be familiar with exponential function, don't you? Jose is not much convinced.
No. I was the one who said that the exponential of
Okay,
Yeah.
of
So-
0 was 1.
this is
So
clear
yes,
for
I'm
you.
very convinced.
This is clear for you. Okay. Now, how can we study the stability? In linear systems, at least. In linear systems. You can study the stability in linear systems by writing this characteristic equation. So by assuming that one, okay, apply the story of the S, and where you have a derivative, you have a S square and so on, and write this equation, and then find the roots. If all the roots have negative real part, you are stable. Otherwise, you are unstable. You see? Even if you have here something. Stability is not affected by that. This something will shake the things, but what is essential for the system is that it goes to zero. This is not a mathematical argument, but I won't use it. I won't use any mathematical argument to show that. Okay? So you can very easily study the stability. Hmm? Okay. Now, suppose that you have a control system. And you put here something which is y dot is equal to minus 5y plus u, and u is here. Okay? And this is why. And you want to study the stability of this stuff. And this is a plus, and this is a minus. Now, you can reduce this stuff, and you have the reference here. You want to reduce this stuff with the S domain. So what you get R K and then I have here something which is that generalized gain, which is what? So apply the S stuff here. So what you multiply by U to get Y?
1 divided by S plus 5.
1 divided by S plus 5. Now, you remember that stuff, that story when we have A and then I do a negative feedback and I put here a B minus plus, and this is equivalent to A divided by 1 plus AB. So what all this stuff from here to Y, this is equivalent to what? So what is A here and what is B?
A is k divided by s plus 5,
K divided by S plus 5.
and B is 1.
So this is, the denominator is
1 plus
okay. Now I can simplify this stuff and get what?
k divided by s plus 5 plus k.
S plus 5 plus K. Okay. So it's the denominator that counts. Now we have this extra signal here. Okay, so it's the denominator that counts for stability. Because you can write, you can go on and write an equation for y in terms of r. No, you can say this. Just to convince you. Y is equal to K R here and S plus 5 plus K. Okay, so S plus 5 plus K. Y is equal to KR. And this is the story that influences stability. Okay, so the exponentials, the exponents are the roots of this stuff here, this part here. Okay, so to study stability, you have to look for the solution of S plus 5 plus K equal to 0. So S is equal to minus 5 plus K. So conditions for the system to be stable. For instance, for K positive, what do you think? Is always stable, is always unstable, depends on K.
It's always stable.
Why?
Because s will be always negative.
Because 5 plus K, it's the sum of two positive numbers, minus becomes a negative number. So for positive K, this is always stable. Okay. And what about K negative?
If k is smaller than minus 5,
If K is smaller than minus 5, then you get
Then-
problems. It becomes unstable. Good. Okay. So the condition is stable if K bigger than minus 5. In particular, if K is positive. Okay. So now you have something that allows you to study the stability of feedback control systems. So you apply this stuff and then you look at the denominator of the so-called closed loop transfer function. This is the closed loop transfer function. This is the open loop transfer function. And this is the closed loop transfer function. Because it's a transfer function because it states the relation between R and Y, two signals. Open loop is between U and Y. The closed loop is between the reference and the output. Okay, so you look at the closed loop transfer function, you look at the denominator and the roots of the denominator, if they must all have negative real parts for the system to be stable. Now, remember that the interpretation of these roots is that they are exponentials. So in particular, you can select K such that the roots are in particular position. This makes the system faster or slower, or even unstable in some cases. Questions? So one way is adjust K such that these roots have gains in some positions. For instance, if I want to have, before I clean up this thing, no questions?
No.
No. I can say transient faster than 2 seconds. So I know that I have an exponential of minus 5 plus K T. Okay. And I can write this in this way, exponential of minus T. And here I have the inverse of that, 5 plus K. Okay. So dividing by the inverse is the same as multiplying by 5 plus K. The advantage is that this is a time constant. Okay, time constant is 1 divided by 5 plus K. So I want this time constant. I want this time constant to be at most 2. So 1 divided by 5 plus K must be smaller or equal to 2. Now I solve this. Okay, this is 1 smaller than 10 plus 2k, 10 or smaller or equal. And now minus 9 divided by 2. So k should be bigger than minus 9 divided by 2. Okay, so you impose, you have the time constant that you get for a given k, and you say, well, this is smaller or equal than my time constant. So my specified time constant. So I solve this inequality and I get k. Okay, so by adjusting, and then you have to say whether this, in this case, it's very simple because this is in the range where k leads to a stable loop. Otherwise, you would have to say and stable. Otherwise, you don't converge. Okay. So you can impose the roots of the characteristic equation to shape the can impose the roots of the characteristic equation to shape the response. Okay. Okay, we have been speaking for 1 hour. I would stop here. Look at these notes, and we will continue. So what we are going to do is this. Well, here we have one gain. So in this case, you just have one root to adjust. It's okay. But suppose that you have multiple roots. So if the system is second or third order or fourth order, you just have one parameter to adjust. Okay. So let's consider the situation. We are going to consider the situation. Instead of feeding back the output, we are going to feed back the state. And we are going to see that by feeding back the state, you can put these are so-called poles. The roots of this characteristic equation are the so-called poles of the system. They are the zeros of this transfer function, of the denominator of this transfer function. The roots of the denominator. And when you feed back the state, then you can impose the poles under certain conditions. You can impose the poles where you want. And this is quite nice. Because you can shape, you impose not only stability, but also shape the response. Okay? Questions? So today we stop here.